All right, so now I'm going to talk about floating point numbers, which are a way for computers to represent a wide range of numbers. Um, so floating point numbers. And if you will, it's like this idea of floating point refers to the decimal point and the ability to move the decimal point backwards and forwards. And that allows you to represent numbers with a wide range of magnitudes more efficiently using just a small number, relatively small number of bits. Okay, so let's see the definition. It's as follows. This is a floating point number system. Okay, so it's a subset of the real numbers R, okay, which we denote by sort of this math bold F, and then a bunch of numbers, B, K, little m, and big M, okay, where B is the base, so whether it's base 2 or base 10 or what have you, K is the number of digits, M is the smallest representable exponent, that M is the largest representable exponent. Then with that in mind, it's like then we say that something is part of this floating sort of point number system if it can be represented as follows. So an element y in f, b, k, m, big M is of the form plus or minus sort of digits d1 to dk in the base b times b to the exponent e, where e is between little m and big M inclusive. All right. So, so you represent some sort of k sort of just fractional digit in base b, and then you have an exponent in b. It's like which ranges between little m and big M, and it could be positive or negative. Okay. All right. So yeah. So if y is in this floating point number system, then it is of this form. And then, so one very, very common standard for this is the IEEE, it's like double precision. So IEEE, sort of double precision. Okay, and if you think of it in base 10, and what it does is that k is 16 digits, m is approximately negative 308, and then big M is approximately 308. So this gives you sort of a rough idea of the kind of numbers you can represent. It's like in IEEE double precision, it's like viewed in base 10. Okay, so it's not exactly that, because really it's like what's happening is that you're representing this, it's like in binary, right? The actual double precision standard, it's like for the IEEE standard, is in binary representation, but it's easier to think of it in decimal. All right, anyhow, so that's just give you a rough idea, it's like of where we're at. Okay. So, so previously we had sort of talked about this idea of round-off error. And the round-off error is basically what happens when you take any number which you want and then you try to represent it as one of these floating point numbers in your floating point number system. So the definition is as follows, that round-off error is the error introduced by representing a real number by its floating point equivalent. Okay, so all right, so that's what's called round-off error, and so let's ask a few questions for this. So let's say that you're given a number y in the rails, right, and a floating point number system. Let's call that big F. You want to find what we call FL of y, right? So that's a map, it's like which takes the rails and then replaces it with its floating point number approximation, such that this is approximately y. So how do you do this, right? So, so how do you construct such a map? So there's sort of two main approaches to this. So you can do chopping, or you can do rounding. So as you might expect, essentially what's happening is that you take this number and you shift it, it's like by b to some exponent, so that the resulting number is, yeah, so that the resulting number is basically between sort of, okay, so how should I say this? So you want to take y and you want to multiply it to b to some unknown exponent, let's call that e, such that this whole thing is in the interval from point 1 in base b, okay, and 1, okay. So that's basically 1 over b to 1, okay. And you can always sort of shift y so that you're in this set. So essentially what that basically means is that you end up shifting y so that when you write this thing in base, and okay, so when you take y times b to this exponent and you write the resulting number in base b, then you will have no integer part. It's like, and then the fractional part, the very first digit is not 0. Okay, so there's a way to always shift this so that that is true. And the way you sort of see this is that you can always write y in base b and then basically move the decimal point, it's like until the first non-zero entry is just to the right of the decimal point. So that's basically another way of seeing it. Anyway, so there's a way to do this, and then once you've done that, then you're in this format. It's like for the floating point number, that y is plus minus, 0.d1 to dk base b times 10 times b to the e. right? And the only difference basically is that it could very well be that this y actually has a longer fractional expansion. And so in order to represent it then as a floating point number, you have to decide what to do with the bits which cannot be represented just using k base 10 numbers. Okay, which is where sort of chopping versus rounding comes in. So as you might expect, what chopping does is to sort of just say, well, I'm just going to ignore everything. And then whereas rounding will say, well, depending on what that next digit dk plus 1 is, I'm going to write this as either dk or increment this by 1. Okay? All right, so let's look at an example of this. So let's say that if your floating point number system is just the integers, right, and you want to find FL of 10.92, right, and you do chopping versus rounding, right? So chopping, as you might expect, is to just sort of drop those digits. FL of 10.92 is just going to be 10, and then rounding is going to be that, well, okay, because of the fact that 10.9 is in some sense closer to 11 than it is to 10, I will write this as 11 instead, right? So that's the difference between chopping and rounding. And as you might expect, rounding is more accurate in general. Rounding is more accurate. Well, it's not in general. Yeah, rounding is more accurate. Okay. Well, at least it's no less accurate than chopping for specific instances. Okay. All right. So anyway, so that's how it's like you could imagine doing the conversion to floating point. As I said, it's like the way to sort of perhaps do this in this setting is to write y, it's like as a base 10 representation, and then imagine moving the decimal point and then incrementing or decrementing the exponent correspondingly so that it still represents the same number. Okay, and then once you have that, it's like you'll generally have some sort of plus minus 0.d1 to a whole bunch of some sort of fractional expansion in B, and then you can decide whether to do chopping or rounding to just reduce it to k digits. Okay, all right. So anyway, so these are two ways of defining this map. It's like from the rails, it's like to your floating point number system. So now let's try to quantify what we mean by saying that rounding is more accurate, right? So in order to do that, we first have to make sense of what, how we're going to measure error in this situation, okay? Okay, so let's say we have P bar be an approximation of P. Okay, so there are sort of two very natural ways of describing or quantifying the error. The first of which is this absolute error. Okay, and so this is probably something you've seen before. I'm going to denote this by delta. So this is just going to be the absolute value of the difference between P bar and P. Then there's also the relative error, which I denote by epsilon. Epsilon is going to be P bar minus P divided by P, whole thing absolute value. So what relative error does is that it scales it with respect to the true value. Okay, so the error being small and large oftentimes is not an absolute thing, right? So if you're, say, trying to measure it's like the size of something which is very small, then it's like a error of say 1 millimeter could be very large because you could be off by a factor of 2 or 4. Whereas if you're trying to measure something very large, say someone's height, then maybe a 1 millimeter error in measuring a person's height is not that significant, right? So certainly there are instances where the relative error is the right notion or of error, it's like which is relevant. Other times it's like you might care also about the absolute error. Okay. In any case, with that in mind, let's go back to this chopping versus rounding issue and think about what kind of errors arise. Okay, so with chopping, you'll find that the floating point value of y is basically y1 plus epsilon, and the absolute value of epsilon is less than or equal to b to the 1 minus k. And then with rounding, the floating point error of the floating point representation of y is going to be y times 1 plus epsilon. And again, the absolute value of epsilon is going to be less than or equal to 1/2 b to the 1 minus k. Okay, so that's a precise sense in saying that rounding is going to give you half, in general, in the worst case, half the relative error you would get from chopping. Okay, so so the round-off error, it's like which is introduced by using sort of this floating point number system, which we talk about. Okay, is best expressed in this case by the relative error. Okay, epsilon, and the error, the magnitude of this relative error is bounded by terms which relate to the parameters of your floating point number system. Okay, so with that in mind, you can introduce what is called machine epsilon. So this definition is for machine epsilon. Okay, so epsilon machine, okay, is defined to be this upper bound, right? So it's 1/2 b to 1 minus k. So this is 1/2 the distance between any 2 points, or I should say the relative distance in this floating point number system. Okay, so for IEEE double precision, which we talked about before, which is what you would use in MATLAB if you do double, right? Then machine epsilon is about 10 to the minus 16. Okay. All right. So anyway, so you'll see this. It's like show up again and again. It's like as we discuss numerical error in our methods. Okay. So I'm going to stop here for now, and then the next thing we'll talk about is how these round-off errors propagate when you start manipulating floating point numbers, like adding them together, multiplying them, dividing them, and so on. And under what circumstances round-off error gets greatly amplified by sort of those kind of elementary arithmetic operations. So, so that's something which is important to think about. So let me just stop here for now.